Morning. Welcome to academic class of Bodri Prasad Group of Institution. I am Sachin Satpathy, lecturer in electrical engineering. We shall discuss about subject CNT, that is circuit network theory, and the topic is Faraday laws of electromagnetic induction. So it is actually practical topic. That means practically we can confirm how the EMF is induced in the conductor. So as in electrical point of view, the Faraday laws of electromagnetic induction is highly essential, as Faraday is our father of electricity. So according to that some apparatus are required for performing the Faraday laws of electromagnetic induction. That is, first is your bar magnet. This is your bar magnet having N and S pole. Another is a solenoid. Solenoid is nothing but a insulating material with coiled wire, which is connected across a galvanometer, which is known as a small voltage measuring instrument. So essentially in Faraday laws there are three things are necessary. One is a bar magnet having N pole and S pole, another is your solenoid, and another is your galvanometer. So in Faraday laws of electromagnetic induction, the first law of the Faraday law states that whenever change of flux, then also an EMF is induced in the conductor. That is, if there is change of flux with respect to time, then also an EMF is induced. That is, we know that every magnet have lines of force that will be arises from north pole and end from S pole. That is outside the bar magnet, but inside the bar magnet it is from S pole to N pole. So otherwise the magnetic lines of force is also known as flux. So this flux, when we place the magnet with nearer to the solenoid, then it is seen that the galvanometer show no deflection. But when the position of the bar magnet gets changed, with respect to that solenoid, that is N pole move towards the solenoid, then galvanometer show right side deflection. If the N pole move towards the solenoid, and if the N pole is moved away from the solenoid, the galvanometer show left side deflection. Similarly, if S pole of the bar magnet will be moved towards the solenoid, then it will be show left side of the deflection, whereas the S pole will be moved away from the solenoid, it will be show right side of the deflection. So from this, Faraday conclude that if the two bar magnet and solenoid are placed nearer to each other, at that time no EMF is induced. But whenever there is change in position of both solenoid and bar magnet, then EMF is induced. So according to first law, whenever change of flux, then also an EMF is induced. That is the first law of Faraday laws. Next, Faraday suggests about the second law, that is the magnitude of induced EMF. How much EMF is induced in the solenoid? That according to Faraday, the EMF induced is directly proportional to the rate of change of flux with respect to time. So according to Faraday, the second law, that is change of flux with respect to time. Let's consider at T1 time flux cross is phi1. At T1 time the flux cross is phi1, but at T2 time the flux cross is phi2. So this is the change of flux, that is at T1 time phi1 amount of flux is cross, and T2 time phi2 amount of flux is links. So according to Faraday, the EMF induced E, that is E, is directly proportional to phi2 minus phi1, that is change of flux, and inversely proportional to the change of time, that is 1 by T2 minus T1. So combinedly we can write E proportional to phi2 minus phi1 divided by T2 minus T1. So this is the rate of change of flux with respect to time. Symbolically, this will be represented as d phi by dt, that is derivative of phi with respect to t. Actually, the derivative is used for decrement of something with respect to time. So here the decrement or increment of flux with respect to time, that is change of time flux with respect to time. So we can now we find E proportional to d phi by dt. So a proportionality make equal when a proportionality constant will be multiplied. So here a proportionality constant n should be multiplied to the expression. So the expression should be now E is equal to n d phi by dt. So now the n is known as proportionality constant. So n, what is n? Now n is the number of turns that will be wound over the solenoid. This is called actually number of turns of the coil which is wound by the solenoid, that is also constant terms. So Faraday only predict the magnitude of induced EMF but does not predict about the direction of induced EMF. That will be later predicted by another scientist called Lenz. According to Lenz, that is the EMF induced is the direction of induced EMF is such that it opposes the very cause by which it is produced. Means the direction of induced EMF opposes the very cause. Very means the change of cause. So here the cause is the relative motion between bar magnet and solenoid. If there is no motion between magnet and bar magnet and solenoid, then no EMF is induced in the solenoid. So we say that if there is no relative motion, there is no EMF. Hence, we tell that the direction of induced EMF E opposes the relative motion between bar magnet and solenoid. So we can write now E is equal to minus n d phi by dt. This is the actual formula for induced EMF in a bar magnet, which negative sign indicates the direction of induced EMF. Thank you.